can implement that. So wonderful. I'll go ahead here and just want to point out we are now entering the 10 a.m. session. This is this one and the next one. It's very fluid. I envision that we roll from one directly over into the other. I don't think 11 a.m. is a hard stopping time, but the idea, what we want to do next is we have some case studies prepared where we not only want to show you live some runs, but these are case studies that we could find in the public domain, and we'll try to match some numbers to see some for electricity. We have a HIP-RA case study. We also have a district heating case study. For the Cornell University project, we've been working a lot on that. So we'll have those, but then in between 11 and noon, we actually have a poll prepared where we'll just put the link in the chat, and then you can actually live give us some feedback on what other case studies you want to see. We have some other examples, some other features that we have example files for that we can run, that we can discuss, because there's too much material just for a one-day workshop. But based on your input, we know what is of most interest to you. And so let me just get started on this one. I'll go back to full screen mode. In this session, we want to talk about these 4 case studies. And we actually have a 5th one also, but on a district heating system. But that hasn't been built yet, so that's still ongoing. So we're not really comparing with some actual data already. But in these 4 case studies that we selected, we try to, we think, based on feedback we received, these are some of the things that people are trying to use geofires for, are interested in. So the first focus on EGS. I know that a lot of people looking at EGS know. We actually later also have some case studies on closed loop that we have prepared that we can talk about. But there's a lot of public information on Project Red. So we did a simulation run on that. So we'll talk about that. Project Cape Station, another one that I know is a lot of people are following that. So we have some runs there prepared, and we'll talk a little bit about that. The third case study focuses on a cogeneration system. I know so far we really talked more about electricity only or direct use only, but you have the capability to do a cogen type system where you may have a topping cycling or a bottoming cycling. You use the geothermal fluid for some electricity production, and then you use it also for some heating. And there just happened to be a colleague reached out, I think, to Jonathan, and he used Thermoflex, which is power plant software. He did some simulations there, and we've been using the same input, do a simulation in GeoFi, see how it compares, and so that's a nice comparison study as well. And then finally, studies we can show you different capabilities. We can show you a little bit the predictive nature with the tool, different applications you have. So then, and if time permits, and I think we with some of the test runs, we should be able to get to all of these, and maybe even also to the district heating case study as well. Well, I'll get started with the first one, which has received a lot of attention lately. And the nice thing about this is that there's a lot of information online, all public information. So we were able to use information that we found from, a lot of it came from this paper, that we pulled information from, and just let's say let's put it in GeoFi, see what happens, see how we can see what of our production temperatures, how much electricity do we expect to generate, what did they find, etc. So that was a little bit the exercise that we tried to do. And maybe not everybody is familiar, so I tried to on one slide show some of the highlights, I think, that are key inputs into geofires. Of course, you need to know well configuration, you need to know well depth, you need to know geothermal gradient, rock properties, and most of the information actually was all available in these papers. And the system that they simulated or that they developed and actually did some testing is for a doublet type system. So this monitor well, we're not really worried about that in GeoFires, but we did some updates to the tool to allow now have horizontal laterals in the system. So originally you only could have vertical wells, but now you have the capability of putting on a system with horizontal laterals. And so we put in the depths for this type of system down to around 750 or 7,500 feet, 7,600 feet, in that range. We know what the temperatures are. It does require, the geofires does require a uniform initial temperature, as you can see from this plot on the left. That was not really what was encountered. Is that a future feature that's needed? Not sure, but we can talk about it later, but we kind of picked an average, about 180 degrees Celsius is I think what we picked, even though their hottest was around 190, but the far end was actually less than 175. So 180 is about an average value for the subsurface system. I think it's about 1 kilometer long. So all that information was fed into the tool. They found about gross. So they didn't produce electricity, but they produced heat, and then they calculate what the equivalent amount of electricity is. And so there are some of their numbers from the paper. We have done a simulation into GeoFires where we then pick electricity as end-use system with this type of configuration. Now, one of the other challenges was that we have to right now assume a constant injection temperature, constant flow rate. We can talk later during the discussion, are these parameters that we need to allow to vary them over time? That maybe we can talk about it later, but in the circulation test that was done, there was a range. I think there was a 200 gallon per minute range that they have, so we just picked average values, which I think it was around 41 kilogram per second. They had a peak up to 60 kilogram per second, but average value was about 41, and I think about around 40 or so degrees Celsius. And these are some of the outputs that we were getting. About the same production temperature. We're seeing about a similar net power. We did have to do one assumption, which is their pumping power. We did not have all the information needed to actually independently estimate pumping power. It does require on some of the like fracture aperture and those kind of things. So the way it works in GeoFires, you can specify a reservoir impedance, which we specified to have a pumping power of around 700 kilowatts or 800 kilowatts. But in counting for that, you get about a little over 2 megawatt net for this type of system. And this project was never designed to really make commercial cost-competitive power. That's really the next one we'll be talking about. But this does allow to compare numbers there. And I can just show you these. This is one of the example files. This is the link is right here. I just clicked on it, and we can then go through just to highlight some of these parameters and some of these results. Most of the ones I already mentioned, I tried to, I've already highlighted. I can maybe show you some key ones. A lot of the economics is going to be determined on how deep you have to drill, what's your temperature, what's your geothermal gradient. They had a very high geothermal gradient, 74 cents, 70 country, and so that's what was encountered there. So that's, we pulled that straight from the paper. Just want to maybe point out, this maybe is a nice opportunity, is that some of the values have units with them and some of them don't. The ones that don't have units, that would be, it assumes the default units, and you can look in the user manual what those are. I think actually if you go to the editor, you can actually see them also right there. For example, reservoir density 28 kilogram per meter cube. However, if you want to specify a value in your preferred unit, a different unit, you can do that as well, where you can see reservoir depth. You can just say it's 7,600 feet. Maybe to kind of show you, I can go away from that and I think it's about 2.3. If you don't specify a unit, it actually will assume back to the default unit, which is kilometer in this case for reservoir depth. Again, that's information we got from the paper. If you're familiar with the project, you may remember the idea was here to do a multi-stage hydraulic fracturing system. What we picked is in the GeoPhires tool, there are simplified reservoir models that are available, and this one here that's being used is this Green Garden model, which assumes, it makes simplifications, but it does assume vertical fractures. You can specify fracture spacing. You can specify the fracture area of your system. This is based on the swept area and based on about 160 by 160 meter so it's a little bit larger than the well spacing. We had to assume some depth. Again, some of this probably are a little bit assumptions, but this is, I think, where the power comes in of a simulation tool like this. Fracture area is a key parameter. Heat transfer area is a key parameter for your system. You can use the tool to estimate what area is needed to obtain a certain long-term heat production. And in this case, they did specify, I think they had about 100 clusters of fractures, or so about 100, that's a number that we specified, about 10 meter spacing. If you run it with this system, we do expect about a lifetime that starts dropping off after about 10 years or so, but this is where I think the beauty comes in. What if you have a much smaller fracture area? How fast does your temperature drop off, etc.? So I think that's where, and we can try it live in a sense. Let's say instead of 160, what if we have a much smaller fracture area, maybe only 100 by 100? The way it works is you can change a value, and then you just go, you click run again, and then it will run it on the right-hand side, and it runs really fast. There's not really, computationally, it's not too difficult of a tool, but you can see we decreased the fracture area, and we all know that has a big impact on heat transfer, and now drawdown starts happening a little bit faster. You can increase it, you'll have longer lifetime, etc. So this is a little bit how I think, how I use the tool, change the parameter, see what happens. I do want to point out that this is nice to have the graph. Sometimes I want to just make my own plots. If you use the user interface, I think the nice thing to do is you can just download it, and all the plot values are stored in the Excel file. So the way to do it is you just download it, and you just click on the file, open it. Let's see if it works here. It actually opens it on my other screen. Let me bring it over. This is how it looks like. So I don't want to go into too much detail here, but all the output values are listed in a CSV file. And if you scroll down, you'll find the plot values as well. These are all at the bottom. For example, maybe you're interested in production temperature. Well, actually, you can see it right here. This is one. And remember, we significantly decreased the fracture area, so as expected, this is going to be much faster drawdown, 100 by 100. I think the target is to have larger fracture, but this is to show you how you can use some of the plots, make some of the plots for yourself if that's what you want to do, if you don't want to use the ones on the user interface. And you see some of the results here, some of the inputs as well. So this is just to close this one. I'll go back to this one. But so I hope this explains how to use it, what we did. Maybe I'll go back to 160 by 160 because the value that I show, we can go to some of the results. It does show also minimum, maximum, average. It does provide a lot of metrics as well. This one in particular, I think it was about 2.21 This is with our flow rate, with the gradient, etc. So this was only a 10-year lifetime. This was not the case study. The next one, we're going to talk more about the economics. This was really just to focus on some of the subsurface model. And we think a subsurface model like this, it probably can help, allows you to do some maybe high-level assessments, first kind of pass. There are much more advanced tools out there, and we would be the first ones to say that. We've used some of those other ones. There's Falcon, there's ResFrag, there's a lot of other tools out there that can do much more detailed subsurface models, and we have the option to use other tools and feed in their output into GeoPhires if you want to go that route. That's definitely an option as well. Actually, that is if you pick number 5, and I'll have an example later where I can show you. You can use you can just provide a time array and a temperature array, and that's what it will do, and it will read that in, and you can use it. But if you want to use some of the built-in ones for EGS, a Green Garden model is like a nice first type of model you can use, get an idea of drawdown, fracture area required, etc. So I'm just looking at the time. There's always a lot, and we can always go back to this during some of the Q&A, some of the discussions. I want to just go back to the slides here and maybe talk about the next case study, because we still have 4 more we hope to get through. This is the next one here is again an EGS one. I just put some of the articles on here where everything was based on, we did this on ourselves, which was just based on public information we found. So by no means we don't share anything proprietary or so. We just based on what we found in literature for a next big EGS project that tries to be the first commercial one, a 90 megawatt type project right next to the 4th setting. And so this is one we thought, hey, why don't we try to do this in GeoPhires, because let's take another look at the economics we can expect. Let's see what it will take to get the target temperatures at the target megawatt output, etc. And so some of the values we assumed here are put on the list here on the left. So it's a little bit deeper, a little bit hotter, and a much larger system from the previous one we just talked about. This time we're going to 200 degrees Celsius. Roughly, again, it's the case. If you look at some of the information that's out there, it's not a uniform initial temperature. We don't have that capability yet. That may require a more advanced reservoir simulator, maybe run it separately and then use GeoPhires for the economics, for example. That's one approach I know some people have taken. But we just, again, assumed a 200 Celsius type system. We have longer laterals, deeper systems. So this time we go to 8,500 feet, about where they're at. Go, instead of a kilometer, I think it's almost 1.5 kilometers long laterals that we're assuming. And it's going to be a much bigger system. It's about, based on what we find online, there's going to be a lot of exploration wells, observation wells, but it seems it's going to be about 12 injection, 12 production wells that are being used, about 24 wells that will be actively being used for the electricity production. We found some information online on the drilling cost. You can use built-in drilling cost correlations, and we'll talk more about those later. But in this case, there's a lot of public information on what some of the well costs are. It was actually less than $5 million per well that was reported, and we just put that in manually. Well cost $4.8 million. In this case, we did not have all the information in terms of what's going to be the flow rates they're going to be producing at. What's the fracture area? So these are some of the things that the way we approach it is more, how much fractures do we need? What's the flow rate needed to get to about 90 megawatt net power output? So that's the way we use the tool this time. This is not being, there's no public production data out yet, not like the first case study we talked about, so that we approach it a little bit different in this case study. And we were especially interested in some of the economics, like what is the levelized cost of electricity, what is the PPA price needed, and so that's the way we are approaching this second case study. I'm just going to load it up here. This is again one that is all, it's all public. We put a lot of the links that that I just showed you, all of the figures. I put in the description. As you on the platform, you can put in a description, and that's where that text is. That we put some news articles, some Stanford Geothermal workshop papers. If this is a case study you want to learn more about, it's all out there. And those are some of the inputs that we did. So it's built up here, and this actually gets me now to a first limitation we ran into with GeoFires that I think we've created an issue, or maybe this is the one we'll actually be creating an issue right now. When you select a reservoir, it assumes you have one reservoir model and you're producing from that one. But in this particular case study, it's going to be a very large well field, and all these wells are going to be next to each other, and so you have all separate type of systems. They're next to each other, but they don't get all the flow from all 12 injection wells combined. And we don't have that capability yet. There's a little work around right now, which is just making your reservoir 12 times bigger, in a sense that then it assumes you have 12 times an identical system in between the wells. So that's the way we approached it, but we have some ideas and some thoughts how we can probably even make it more advanced and allow you have multiple type of systems in your same larger geothermal area. Anyway, maybe some topic for discussion later, but just want to put that out there. We wanted to use the built-in tool, and that's the way we kind of went with that. So in this particular case, I think, as I mentioned, when you have the 12 injections, when you have the 12 production wells, we found you need about 98 kilogram per second to get to 88 net megawatt electric, which is a little bit higher than, and I know they wanted to go higher, it's a little bit higher than the Project Red one. It's actually still lower than what the EGS Earthshot target is. I think there it was a 125 that was considered there. So I think these are all these are on the higher side, but that's what we want to get to. So I think these are realistic numbers, and definitely in hydrothermal systems, there are wells that are much higher than this even that are producing. So that's the value that we found. So this is in a sense a sensitivity study that we did. What's the temperature, the flow rate we need to get to the target megawatt electric? We assumed we manually specified the well cost, and so I just want to point out how you do that. You can override the built-in correlation. Every cost parameter, you can either use a built-in correlation, you can use a multiplier of the built-in correlation, or you override all of that and you say, well, drilling and completion capital costs come at 4.8. This is $4.8 million. And I can also go to the editor. You can find the same information. Let me see. It's probably under economics, actually right here is that parameter. So that 4.8 is something we manually forced because we found it and we put it in the description. There is a news article right here where it talks about $4.8 million. And so that's the way, and then you can see right here, but this assumes no 24 wells, so this gets multiplied with 24. We did, I think some of the stimulation costs, actually manually, I think this is probably a little bit too low. It would be good to, for example, hey, they're gonna be doing a lot of stimulation, maybe even both injection and production well. You can then just change the parameter, you run it. It runs in a few seconds. We kind of increase the cost a little bit there. This is a very unique system, and so we kind of like probably the built-in correlation isn't really, it assumes a stimulation cost per injection well. That's what the default is. I think they probably are going to be stimulating all the wells, but I don't have all that information. But the tool allows to play around with it and, for example, see we assume the 15-year lifetime we do with this type of system can maintain a long temperature, but then slowly it starts drawing down over time. I want to talk maybe a little bit about the electricity. about the economics, there's different type of economic models that are built in. You can do a very simple levelized cost model with a fixed charge rate, very simplified. You could do, if an LCOE is your output, you can do a standard levelized cost model. You can also calculate a levelized cost of energy with a little bit more advanced model, a binary cycle type model. It's the bicycle model abbreviated here, but it doesn't require, that's the name, we didn't develop it, that's the name that the model has, but it does allow providing some additional information, tax rate, if you have an investment tax credit. We actually, right now it's still at 0. This probably is not representative. Maybe we should put probably 0.3. Yeah, I think 0.3 is probably what the investment tax rate should be, but you have to specify tax rate, etc. So it provides a little bit more detailed analysis there. But I also want to point out that we have other type of metrics that we calculate. They are summarized here in economic parameters and some of those outputs. As you can see, there's an NPV calculation, there's an IRR calculation, because we got some feedback that an LCOE is probably not always the preferred output. Some investors want to have an NPV or a different type of metric, and those are grouped here. There's different parameters that go with that now. If you want to calculate an NPV, you need to specify what is your price of electricity that you're selling at, and there are different parameters here. We specify maybe even high. We can go a little lower. This does assume what's your starting rate, what's your end rate. You can have some escalation in your electricity price. That's what this parameter, right, what these get to.
That ending price actually wouldn't.
It actually uses, yeah.
Just a cap.
That's true. You're right.
It wouldn't actually reach.
We specify an escalation rate. Yep, that's right. And I think the way this is actually every year it assumes with this amount you add it up. So that's true. This is a cap, but 15 cents per kilowatt hour. It is quite high. What if it's a little bit lower? So that's the kind of way you can then change the parameter, rerun it, and let's go back to now. Your PPA lower, NPV dropped. This one still has almost $200 million. With that, of course, your IRR has dropped as well. But for example, your LCOE hasn't changed. That is not dependent on that one parameter. That's your break-even price. There are different parameters that impact that, and it's probably beyond the workshop to go into each individual model. But if there are questions, we can talk more about that. And some of that is covered in the user guide and the papers that we referenced. So that information is there. And I do see a quick comment there. That's a good point. I do want to give credit to Malcolm, who's building a lot of these economic models, and so that's about 3% escalation rate that's there. So that's a reasonable number for sure. So anyway, let's see. I think we're at 10:35 Mountain Time. We still have some exciting case studies. We can revisit these. This may be a good moment to start the next case study. Wonderful. So the next one, case study 3, is it's one on a cogeneration system. So we do wanted to include one that's not just electricity, not just heating. A lot of our examples are focused on that. This one is a cogeneration system, and I'm going to bring this over because it's very interesting information. This was a very detailed power plant model that was developed with a software tool, Thermoflex. It's a commercial software. I think you should be able to see my screen. What we did here is we just want to point out we have a simulation that was done independently by a colleague or friend, in the sense it was a 250 degrees Celsius system, 60 kilograms per second, so quite high, good resource conditions. This is an example where what they simulated is it goes through a first conversion. This actually is going to be a steam turbine here, and then secondly, there is more heat left in there. There's going to go through an ORC type system, and then thirdly, with the remaining heat that's in there, it goes through a district heating network, and then it gets reinjected. So at about 55 degrees Celsius or so is your reinjection temperature. This was a very detailed simulation, much more detailed than GeoFires will do, but this gets you about 8.1 megawatts is the combined net power. I don't know the breakdown. I guess actually it's right here, maybe about 65% comes from the ORC, the remaining from the steam turbine and the generator. And then finally, the district heating network gets about 8 megawatt as well. So what we try to do is like, hey, we thought this will be an interesting case study. Let's see what GeoFires comes up with. Let's see what some of the economics could look like. And this was a nice exercise to showcase the Cogen model and to see how do we compare with Thermoflex. I do want to put out there up front that GeoFires does not do as detailed of a power plant model as was done in Thermoflex. The reason is that we have to pay, when we pick the Cogen model, you pick, right now in GeoFires, you pick one power plant and then you pick a district heating or a heating application. We don't have the option yet to pick two power plants in series in a sense, but a workaround for that one right now is let's pick a double flash power plant. It's a little bit, they in a sense have like a single flash and an ORC approximately, but so let's go to a more efficient power plant. So we picked a double flash one. But this is to showcase, we'll do with the high temperature, we do power production, and then with whatever the heating that's left, we do district heating. I do want to point out, you have different configurations for Cogen in GeoFires. You can have a bottoming cycle, you can have a topping cycle, you can also have a parallel cycle where you break up the fluid flow rate in two parts, and both applications see the high temperature. But I think the most common is probably use all your fluid at high temperature, first make electricity to get the best efficiency out of it. And then secondly, with whatever heat is left, you make some heating after that. The link is in the chat. If you're interested in Cogen, we have it open here on the screen. The way you pick a Cogen is you can go to the end-use option, and right there are different type of configurations. If you pick one, it just picks electricity. If you pick two, it just picks heating. If you pick heating, then you also need to pick what your application is. If it's not direct use heating, and I'll show that later, you can actually go to plant type and pick heat pump or district heating or absorption chiller, etc. But in this case, we are picking a Cogen topping cycle, so that actually internally that had a value of 31 for that metric, for that parameter. But now if you look at the user interface, there's some extra information, so it's a topping cycle. The difference between 31 and 32 is once you have a Cogen plant, you have different streams of revenue in a sense. You have heating is an end-use product, you have electricity is an end-use product. The difference between heat and electricity is you have to then specify, do you want to calculate an LCOE, do you want to calculate an LCOH, like how is that all being treated? So that is done with that parameter. It doesn't have an impact on NPV and all that. You can still specify what is your electricity rate, and I see we didn't specify the heat sale price, so it assumes a default value there, and we can take a look what that is and even change it. But so these are some of the main parameters. And as I mentioned, we assume a double flash plant to represent the power production. The way GeoPhires does it now, it has pre-calculated correlations for power production for different cycles, including for double flash, and it has an estimate for what is your outlet temperature from your double flash plant, how much heat is still in your system before you re-inject it. So that's the way it can calculate what remaining heat is in your heating. And with this setup, with the temperatures that they have, it gets you about the 250 degrees Celsius that we're producing, or that the bottom hole temperature is. We find, so this gives you about a little over 8 megawatt electric, a little less than 8 direct use heating. And so these are, I mean, we were pleasantly surprised. We were getting very nice, similar results. So maybe I'll go back. They found we have a little bit more electricity or a little bit less heating. So we're also not doing the exact power plant, but it allows your tool to do these type of simulations, high level as well. Of course, if you then go to do an eventual design of this type of system, you probably need some more advanced software like Thermoflex. I did see a message in the chat. It does look, I haven't used that before. It looks like very expensive software, but there's probably other software out there as well, where you can do very detailed component by component model. That is not what GeoPhires does. It has pre-calculated correlations. It does Aspen Plus type simulations for some of these plants, but then it uses correlations where you can specify a flow rate, a temperature, ambient temperature. So you specify a few metrics, and then it uses correlations that are built in. So that's the way it does. But we were getting some nice similar type of output as with the other tool. Thermoflex, it doesn't. There was no economics on here. You cannot really turn off economics in GeoPhires. It will always calculate economics as well. In this particular case, it will use. Let's see. It did assume just one injection, one production well. I think this was 60 kilogram per second. All very reasonable numbers. I think we had a 40 C per kilometer, so we're going pretty deep. We didn't really focus in this model on the subsurface simulations. We just assumed a more simplified model, a thermal drawdown model, where we may have a little bit of drawdown. So we in a sense assumed a generic type model where we maybe history match a field, or maybe try to match a reservoir simulator output. So if you pick that one, you just pick model 4. And let's see, when you pick model 4, you can specify some drawdown. The way to do that, the easiest one is there's a lot of parameters. As you can see, let me just quickly go. I can actually right there. I'm just going to type in drawdown because I know that's a required parameter. And actually, we assume no drawdown in this one. So it's not 100% representative. We didn't know the subsurface conditions. But if you want to have some drawdown, 1% per year or so, you could do that. It is, or maybe even 0.5%. You just specify that parameter, and then it will use it. And it was going to change a little bit the economics. We're going to start seeing actually this red curve start slowly going down, and that's just a simple representation of a subsurface model. But that was not the intent of this exercise. But just want to show, we have a little bit of drawdown now, so the NPV as well dropped. But it does assume, I think it's quite a deep system that we have. The well drilling, then we assume to build in geovision type correlation as a function of the depth. If that's something you want to look at, so for example, you can just type in well, and we can go to economics. So we did not manually force the well cost, so it actually does assume a built-in correlation. And we have a lot of different correlations out there. The reason why is that, well, first of all, there's so much uncertainty in drilling costs, and there's especially so much uncertainty what's future drilling costs going to be. And your drilling cost also depends a lot on, do you have a vertical one? Is it open hole? Is it cased? Is it deviated? So a lot of these ones that you see here, they are based on some of the GeoVision type correlations. They were updated, I think, in 2022, so we've had with the updates right now that are in that. These are dependent on the depth that you're drilling to, and you can specify the base case, it's the more advanced, or if you don't want to use it, you manually specify what your drilling cost is. In this particular case, we assume a vertical one, large diameter, but it's an intermediate one, so it's a little bit more aggressive than the base case, and we may actually be, with all the recent advancements or decline in drilling costs, the base case is probably a little too conservative at this point, so this is, we felt was a representative one. Anyway, so it allows you to play with all that and to see if I change this parameter, what happens to the cost, etc. The one I wanted to talk about here, I'll go back into full screen mode, is the project at Cornell University. Because there's a lot of, they've done a lot of case studies there. There's a lot of ongoing activity there. I also want to highlight, in a sense, with the history, as you may know, a lot of the GeoFIRES development happened at Cornell University as well, in the version 2 towards version 1 towards version 2, when the heating got built in, the district heating got built in. I see some of the Cornell folks are on the line, so it's great that they're participating as well today. I just select, we've done a lot of case studies in GeoFIRES for district heating, and there's a lot of information out there for the Cornell one, so I just picked one. I wanted to show you one. I just have one slide on some of the background in that this case study, so we're not comparing yet, unlike the previous ones, we're not comparing here to a different model. We're not comparing to, let's say, existing production temperatures. We're a little bit in an earlier phase here, but we do have a well that was recently drilled, which is shown on the right, the 10,000 feet well. So some of the values we were able to get from the Kubel well, the Cornell University Borehole Observatory well, in terms of temperatures. We know some of the rock conditions, etc. So we were able to use that information as some of the input. But then we were kind of able to play with some of the cases, with some of the configurations. There's a lot of different examples that you can run with or without a heat pump, with or without a district heating, or how you're going to use a district heating system. So I just pick one. I just want to point out there is an existing district heating system in place, and some of it's hot water, some of it is based on steam. I know it's under construction to migrate over from the steam to a hot water-based system. But in a sense, the geothermal district heating is like the last piece of the puzzle to go to carbon neutral at the campus there. And so that's what the whole overarching objective here is with geothermal for the campus. And so the case study that I picked is a little bit of a more simplified one. It's one where I wanted to show you the GeoFIRES capability, where you feed GeoFIRES an hourly heating profile, and it will then consider a peaking boiler plus geothermal. So the nice thing about this case study is that we have a lot of that surface data that's required available. In this particular case, we knew how much heating is required for the campus. It's from a few years ago now, but it's about a 10 megawatt base load, but it goes up. There's some peaking that goes up to 80 megawatts, and then it goes down again. And so this follows the university's fiscal year. It starts in the summer, but this is the winter peak right here, so it goes quite high. And the thought is that we're probably not going to build a geothermal system to cover 100% of the heating, because you would be oversizing it. You would end up with a low capacity factor, because most of the time you would not be using all the heat that's available to you. And that's where those peaking boilers come in. Right now, we just use natural gas as peaking boiler. You could assume maybe biogas or so for that. There's different type of models you can do. But in this particular case, what we just want to show you here is I went down to assumed an EGS type system again. So this is the target that we're going to be in the bedrock. This particular case, I went a little bit deeper. I went to 3.5 kilometers. The well that was drilled was a little bit shallower, but so we may be going a little bit deeper, still TBD. But you get about 94 degrees Celsius at that point. And in the case study I'm showing you here, there's no heat pump yet, There is also one potential design is using heat pump coupled with geothermal. In this particular case, I'm not using heat pump, but so I'm bringing it down to around 40 to 50 degrees Celsius, not quite as low as you may get to 20 degrees Celsius. But what GeoFires does then is it will simulate this early profile, but it does it over its lifetime because it can change over year to year if you have some drawdown. And this actually is now an average plot that it shows. This is an output from GeoFires where it calculates we're using geothermal for this particular case as two doublets that we assumed, 50 kilogram per second, 50 liter per second. I think we've been looking at different cases, 30, 40, 50, maybe even 60. I believe 60 is what was seen as Project Red. They want to go higher there now. This case may be a little bit smaller system. We want to make sure we don't have too fast drawdown, but 50 was assumed here. And with this type of configuration, two doublets, that would cover pretty much the base load, a little bit more even, but then the remaining is still natural gas. And so you can play with this. This is online as well. Let me just go. I think that it's in the chat already, but the link here, if you run to it, you can run the district heating system module on the user interface. What it needs though, and I wanna point that out, is you need to provide it a CSV file with that heating demand. And so in this particular case, we've uploaded that one. This is public information. This is an hourly heating profile that it's stored on the GitHub. You can actually find it there. It's under the examples folder, and we need to specify the file path. This is the relative file path to get to that heat demand profile. I just want to point out, and I think we maybe have time later to talk about it as well, if you do not specify, if you don't have the heat demand available, we build in some options to let GeoFires estimate it for you based on the number of buildings and the climate zone you're in. There is some information, so this becomes high level at that point. Ideally, you have it measured somewhere and you can use it, but if you don't have it, you can either give it a weather data profile, something like TMY3, for example, or an actual weather type file that you have available, an early one. You can give that one as well. This is based on one or two. We probably don't have time to go into all the details here, but you can also give it a weather profile or tell it which climate zone it's in. And then you also need to specify how many households am I trying to, it assumes it's a residential type system, how many households am I trying to serve here with the system, and it will assume some standardized heating per household type numbers that we pulled from EIA type data sets, etc. A lot of that is public information that we try to get. You can give it hourly, you can give it daily, but that's the way when it tries to estimate that type of profile that it needs to know, that it tries to get to. But you can manually provide it as well. The second thing I want to point out is once you have a district heating system, it also tries to estimate the cost for the district heating system. In this particular example, we have an existing district heating system. I believe we actually just then manually put it to 0. I'll try to see if this is the one example where we actually did that or not. But if you don't provide it a district heating cost, you can let it estimate it based on the road length and $1 per meter piping length. So it just falls back on some default correlations. Just want to make sure it won't crash, but it becomes more estimate. Ideally, you have maybe a vendor quote or so that you can provide, build it in, but you see some of the parameters that are being used. Actually, just one point, I specified it to 0 for this case study, but if you look at example 12, which we may get to later, we did not specify to 0. In this case, we have an existing heating network. We say we don't have the cost, we don't need the cost for that. But if you don't have an existing district heating network, let me see if I can quickly get to that. You can specify things like road lengths, specify, in this case, for example, specify a district heating road length of 3 kilometers. It will just use that. In this particular case, that input parameter is neglected because I overrode it with I force it to be 0. But if I don't force it to be 0, it will look for these other parameters, those keywords in the input deck. And 3 kilometers is one of them. $1,200 per meter is the cost. Again, I think 1,200 is a representative. I think that it's close to the default, maybe $1,000 per meter or so default. So this is the cost for building your district heating network. So these are all additional parameters. And they will start showing up then into your output results as well. For example, district heating system cost, right now it's 0 because I told it to be 0, but it will then have a value if you don't force it to be 0. So this is a little bit what this end use option does. Maybe very quickly, how do you select that? Well, the way to do that is you specify it under the plant type. So you need to say, I'm not going to do electricity. I don't have a Cogen. I have a heating application, and then number 7 is the district heating. That's the way you select it. The case study is one of them. If you go into the examples, there is even another one, number 12. District heating is another district heating example as well. The last thing I want to point out here is I thought this may be a good moment to briefly show you, if you don't want to use the user interface, you can run it also from an IDE on your local machine. PyCharm, I think it's a very popular one. I think a lot of the users, they use PyCharm. The problem is PyCharm, it's actually not allowed on NREL machines, and I don't think it's not allowed on DOE machines. So we are using VS Code instead, which sometimes a little bit more buggy, but you can run it in there as well. And I think you can even run it into Spider as well. I'm not sure if the whole Git interface is there, but with VS Code, we have it all linked also to the GitHub. And the reason why I quickly want to show you is the figure on the right, it is GeoPhire's output, but right now, if you run it in the user interface, you won't see this figure. You actually have to then run it locally on your machine. And in this particular case, let me see if I have it open. I can probably just bring it over. You need to specify the folder, and right there, this is a figure that's being generated. The figures that I showed you, it gets generated when you run it locally. Just in a sense, and an FYI, so you're aware of that. It generates some other figures as well if you pick that as your output. But in a sense, everything you see here, in a sense, it's a reflection of what's on GitHub. You'll see the same folders. You'll see the same files. I have it linked to my branch, which is fork, but it all links back to the main NREL GitHub folder. And you'll see, the code is all here in the GeoPhire SRC file, the one that I've been using. The examples is as well all in the test folder. They are all stored right there. So I don't think we have time to go into too much. If that's a request, we can definitely do that. Right now, I think this is a good moment to maybe do a little pause here. I think